Hi students, today I am going to explain about transistor hybrid parameter model. Before going to start this lesson, what is the main purpose of this hybrid model or H parameter model which is used for transistor? Whenever we connect any two-terminal device like a diode in a network, so either it is in forward bias and reverse bias, we can equivalent diagram for diode which is equal to current voltage in series with the internal resistance small rf in series with this diode symbol. When we replace these three elements in the place of diode so that we can accurate current flow in the network or voltage drop across the diode across the internal resistance, we can analyze it by using this diode equivalent circuit. Similarly, when we take the transistor connected in among any configurations like CE configuration and CB configuration and CC configuration, then we have to analyze this transistor behavior. We must ensure the transistor replaced with some equivalent circuit diagram. It is not that simple of diode, as we used diode equivalent circuit in the network. So it is a three-terminal device, so which is connected in different fashion. So we will see now how this three-terminal device connected in the network. So we know that the configuration which helps us how connected this transistor in a network by considering one terminal is common and the remaining two terminals connected at the input side and at the other output side. So when one terminal is common, then the remaining two terminals act as input and output terminals. So it will be easily understood by the transistor in the network. Now we will see what are the different models which are used to analyze the transistor in the networks. This is the hybrid model. Why it is called hybrid model? And then this hybrid model which can help us to understand the behavior of the transistor. Basically, there are different types of models like Z parameter model and a Y parameter model and a H parameter model. These are called two-port network model. So when we see first what is two-port network model. So if you take any nonlinear device, so we can consider a two-port network which consists of two ports. One is input and one is output port. So here input port we can represent it with 1 and 1 dash, and output port we can represent it with 2 and 2 dash. This kind of representation, a port which is available at the input side is called input port, a port which is at output is called output port. When we consider any nonlinear device, especially a transistor, this nonlinear device can be assumed that there is a linear device while applying for two-port networks. So when we take this nonlinear device, transistor can be considered as linear circuit for the small signal, so that we can apply this model, two-port network model can apply to transistor. In among these two ports, one is 1 and 1 dash input side input port and a 2 and 2 dash at the output side. So here in the transistor, three-terminal device can be connected in three different configurations: CE and CB, CC configurations. So these configurations, one terminal is common. So that input terminal is treated as one input terminal with respect to ground terminal, common terminal, and output terminal is at output side with respect to the common terminal, so that we can connect a three-terminal device in a two-port network model. There are four important parameters in the two-port network model, which are called input voltage, input current, output voltage, output current. This input voltage we can represent it with, it is a port 1, so we can represent it with 1, V1. And input current, so input port is represented by 1, so input current is represented I1. Similarly, I2 represents the output current, and V2 represents output voltage. So two voltages and two currents, which are input side V1 and I1, output side V2 and I2. In this case, the generalized linear circuit two-port network model, there are among 4 parameters. V1, I2 are dependent variables, and V2, I1 are independent variables. So we can write this V1, I2 in terms of V2, I1 in the two-port network model. So this is the relation between voltage and current in H parameter model can be represented with in this hybrid model, which consists of both Z parameter model and a Y parameter model. So here the parameters represented in this H parameter can be combination of both these Z parameter and Y parameters. So we can combine together. We can call it as a hybrid two-port network model. So now, what is the generalized dependent variable equation for the hybrid model of any linear circuit? Let us take V1, I2 are the dependent variables. So first we take the V1. V1 is equal to H11 I1 plus H12 V2, where I1 and V2 are independent variables. Similarly, another dependent parameter I2 is equal to H21 I1 plus H22 V2. These for H11 and H12, H21, H22 are the hybrid parameters. These parameters which will help us to understand the behavior of a linear circuit that we can apply this hybrid model. This can also be represented in matrix form, which is equal to, take the dependent variable V1, I2 on left side column matrix, which is equal to H parameters, which are called H11, H12, H21, H22, multiplied by independent variables I1, V2, multiplied this I1, V2 column matrix, so that we can get this H parameter equation can be represented in matrix form. Now, how to find out these H parameter models in two-port networks? Let us consider a two-port network which consists of 4 variables or 4 parameters, and these 4 variables which are called input voltage and input current and output voltage and output current. So by considering one port is constant and find out the other port parameters. So here, in order to find out these 4 parameters, H parameters, we can keep the one port constant to get the other port. Let us find out first parameter. So here we can divide it into 2 parameters by keeping output side constant, and we will get 2 parameters, and by keeping input side constant to get other 2 parameters. Let us see what are those 2 parameters by keep constant at output side. So here output variable in this equation, output variable is called output voltage V2. So by in 2 equations, output variable is now called V2 and input variable is called I1 on right side. So by keeping output variable constant means V is equal to some 0, which means short circuit. So by keeping The short circuit of the output port of two-port network as shown in the figure. So keep the output port short circuit. Keep the output port short circuit. By keeping output port short circuit 2 and 2 dash, we can find out input H parameters in the equation. So by keeping output port constant in the equation 1, V1, so when it is 0, so second term gets 0, we will get first H parameter, H11. And then second time when we kept output voltage 0, V2 is equal to 0, in this second equation we will get this H parameter. So that H11, H21 are the parameters which we got while the output shorten, output circuit short, the short circuit of the output port. So that is the first parameter, which is called short circuit input impedance. Short circuit input impedance means it is the ratio of input voltage to the input current at a short circuit output port. So from this equation 1, when we shorten the output port, V2 is equal to 0, the second term gets 0. So the V1 is equal to H11 I1. V1 is equal to H11 I1 plus second term is gets 0. Then what is H11 means? It is the ratio of V1 divided by I1. So the ratio of V1 by I1. What does it mean, V1 by I1? So in the numerator and denominator both having 1 and 1. That means port 1. So ratio of V1 by I1 means input port voltage by input current port. Input port current. So ratio of V1 by I1 is the simple basic meaning of impedance or resistance. If it is complex form, it is impedance. So it is input impedance because V1 by I1. So both voltage and the currents belongs to input port, so that it is input side, and it is a ratio of V by I is called impedance. So it is a input impedance. How can we get this input impedance? By shortening the output voltage. So that the parameter is called in written in words short circuit input impedance. That first H parameter is also called short circuit input impedance. That a formula for input impedance H11 is equal to ratio of V1 by I1 at V2 is equal to 0. And when we see the same another parameter by keeping output voltage 0. So when we take the second equation, H parameter model equation, I2 is equal to H21 I1 plus H2 to V2. When V2 is equal to 0 in this equation, H22, the second equation, I2 is equal to H21 I1 plus H2 to V2. By V2 is equal to 0 means second term gets 0. When it is gets 0, then only we have V21 into I1. So what is the H21? It is the ratio of I2 by I1. Ratio of I2 by I1. So what does it mean? Here, first term, numerator term is represented with suffix 2 and denominator term represented with suffix 1. So where I2 nothing but it is the current belongs to port 2 and I1 is nothing but current belongs to port 1. So when the ratio of current by current or the ratio of output current by input current, it is represented by gain, current gain. The meaning of gain is output by input. The meaning of gain is output by input. When gain is nothing but output by input, it is a current gain. When current gain, it is a current output by current input. So I2 is the current output because it is output port current I2, and input current, it is an input current I1. 1 represents the input port. So ratio of output current divided by input current is called gain. So current gain. H21 is called short circuit current gain. Why it is called short circuit? It is output port 0 or short, and then ratio of I2 by I1, which is called current gain, short circuit current gain. H21 is called short circuit current gain. Now, when we take the other two parameters, how can we get other two parameters in the H parameter model? By opening the input port. Why opening the input port? In first case, this V2 parameter from two equation, the second parameter V2 is equal to 0 in first case. Now, second case, I1 is 0. Second case, when I1 0, whenever current 0 means it is open circuit, voltage 0 means short circuit. So in this case, by keeping I1 0 to get H21 parameter, by keeping I1 0 in the equation 2, you will get H22 parameter. This is called open circuit parameter, open circuit. So the circuit diagram for open circuit of input is by opening the input side and applying the output voltage V2 and I2 current. So when it is open, so the I1, by considering I1 is equal to 0, but open terminal having voltage V1, it is existed, but I1 is 0 because it is open terminal. What is the another third parameter can be calculated from this open circuit? By considering input port is open circuit, which is called reverse voltage gain. Open circuit reverse voltage gain. In this equation, V1 is equal to H11 I1 plus H12 V2. Whenever it is gets 0, by considering I1 0, so you will find out H21, which is the ratio of V1 divided by V2. When V1 by V2, what is V1? Port 1, input port voltage. What is V2? It is a second port, output port voltage, output voltage, input voltage. Numerator is having input port and denominator having output voltage. Numerator having input voltage, denominator having output voltage. As we know that this gain, general definition of gain is equal to output by input. Whenever it is current gain, current output by current input. Whenever it is voltage gain, output voltage by input voltage. But it is reversed. The ratio is input voltage is on numerator and output voltage is on in the denominator. So whenever it is a replica or a reverse of this gain, so we will call it as reverse voltage gain. So the units for current gain and voltage gain is constant. So then no units for gain, for current gain and voltage gain. So it is a reverse value of V1 by V2 in the equation H21. We can call it as open circuit reverse voltage gain. Because of I1 is equal to 0, it is open circuit, and it is a ratio of V1 by input port voltage by output port voltage called reverse voltage gain. Another parameter we can calculate from this H parameter model, which is called open circuit output admittance. Open circuit output admittance. So what is open circuit output admittance? When we take the second equation, I2 is equal to H21 I1 plus H22 V2. By considering I1 0, this term gets 0. So you will get H22. It is the ratio of I2 by V2. So ratio of I2 by V2 by considering I1 is equal to 0. I1 0 means open circuit. And I2 by V2. So it is a 2. 2 represents the both are output side. So that's what output. And I by V. We have a formula, basic formula. R is equal to V by I. And 1 by R is equal to I by V. 1 by R is also called admittance or conductance. So we can call it as output admittance. It is called output. Why it is called output? By considering output current by output voltage. Ratio of I by V represents the admittance or conductance. So H22 is equal to open circuit output admittance. So these four parameters H11, H12, H21, H22. So these four parameters: short circuit input impedance, open circuit reverse voltage gain, short circuit current gain, open circuit output admittance. So these four parameters which are used in hybrid model. So here if you see this first parameter impedance, units are impedance. Second parameter reverse voltage gain, no impedance. Current gain, no impedance, and admittance. So here y parameter units, h parameter model units, so that we can combining these together, we can call it as hybrid parameter. Now, when we consider this h parameter equivalent network of the two-port network, so far we find out the four parameters, h parameters, h11, h12, h21, h22. When we consider these four parameters, and the equation for this two-port network model can be draw the equivalent diagram for these two equations. So when we consider these two equations, so in order to draw the h parameter equivalent network of a two-port network, first we have to write the equation of voltage and current. We know that V1 is equal to H11 I1, H12 V2, I2 is equal to H21 I1, H22 V2. Here V1 and I2 dependent variables, I1 V2 independent variables. This equation 1 can be represented as a circuit based on Kirchhoff voltage law. By focus on this equation 1, by looking equation 1, it is a source voltage is equal to drop across individual element like H11 I1, H12 V2. H11 is called impedance. Current multiplied by impedance is called voltage, and H12 reverse voltage gain no units multiplied constant multiplied by V2 is nothing but voltage. So by adding two voltages V1 plus V2 is equal to V2 plus V3, V1 is equal to V2 plus V3 means source voltage is equal to sum of individual voltages, which is look like a Kirchhoff voltage law. When the equation is looking it is Kirchhoff voltage law, we can equivalent diagram for this equation 1 can be considered as a simple series network or simple Thevenin's network. So what is the equivalent diagram or equivalent circuit for this equation 1 is, so V1 is equal to source voltage is equal to H11 I1 plus H12 V2. So we can consider that this is V1 is nothing but source voltage, and H11 nothing but impedance multiplied by current. So I1 current flow in this network multiplied by this H11, it is a impedance. So we can represent with impedance, and plus the voltage drop across plus some voltage with independent voltage. That independent voltage represented by this symbol. So here this independent voltage is called H12 and V2, H12 V2. So if you apply the Kirchhoff voltage law, algebraic sum of all voltage is equal to 0, or source voltage is equal to sum of individual voltages. So V1 is equal to source voltage, V1 is equal to current into impedance, nothing but voltage drop, H11 I1 plus H12 V2. So we can get the Kirchhoff voltage law. So that we can equivalent representation of equation 1 can be a simple series network, and also which is just like a simple Thevenin's equivalent diagram. And similarly, we can apply equivalent diagram for second equation. It is look like a I2 is equal to H21. What is called H21? What do you call? H21 is equal to reverse forward current gain. Current gain nothing but no units multiplied by current, nothing but current, plus H22 admittance. So we multiplied by admittance 1 by R, V by R nothing but current. So that total source current is equal to sum of individual current elements, current source. So source current is equal to sum of other currents. It is like a network which can apply Kirchhoff current law. When any network apply Kirchhoff current law means a total current we can divide it into two elements. This is two elements. Total current I1 and plus I2. This network we can apply Kirchhoff current law. So similarly here also equation 2 can be represented with can be based on the Kirchhoff current law. So Kirchhoff current law, we can consider that from the current I2, this current I2 flowing through the resistor in parallel with the current source. That current source represented with H21 I1. This is the H21 I1 is the H21 is the unit. H21 is the current gain. No units multiplied by I1 nothing but it is a simply current source in a dependent current source. When it is a current source represented with this one with arrow, and in parallel with the resistor, whenever the current flowing through this one impedance, this admittance, so we have a output port V2. So V2 into 1 by this output admittance like 1 by R, V2 by R nothing but I. This current flow in this one is something H2 to I2 to this one is I1 one like. So the sum of these two currents is equal to I2. So we can represent the equivalent diagram for equation 2 is like Kirchhoff current law. So the diagram which consists of current source, dependent current source, and in parallel with the resistance, which is called admittance. When we combining these two parts of the network, we get the H parameter equivalent circuit diagram for two-port network, a generalized two-port network. So from this part, nothing but a KVL for the equation 1. This part, nothing but representation of KCL, Kirchhoff current law for the equation 2. So a voltage V1, input port voltage V1, and in series with the resistor and in series with the voltage source. A current source in parallel with the resistance across this output port. So this is the representation for equivalent diagram for H parameter model. When we apply the Kirchhoff voltage law, when we apply the KCL law, Kirchhoff current law, so that we can get the two equations. When we apply the Kirchhoff voltage law, we will get V1 is equal to I11 H11 or H11 I1 plus H12 V2. We will get equation 1 and apply the Kirchhoff current law from the output loop. I2 is equal to current flow in this loop, current flow in this loop. This current flow in this loop is nothing but H21 I1 plus here H22 V2, where V2 by R nothing but H22. Here admittance. Admittance nothing but 1 by R. So V2 by R nothing but current. So here the equivalent beautifully representation of this two-port network equivalent diagram. Before going to apply this two-port network to the transistor, how this a device, linear device having two ports, input and output ports 1 and 1 dash, 2 and 2 dash, this linear device equivalently represented with the 4 H parameters H11, H12, H21, H22. We can represent it in the form of KVL at input side and KCL at the output side. So this equivalent circuit diagram for hybrid parameter model, which will help to make the transistor equivalent in the networks. So this hybrid parameter can be applied to transistor also, because when we consider the transistor here is as a linear network, so transistor also, when we connect to one terminal is common and remaining two terminals, one is input and other is output, we can analyze this transistor as a two-port network model. Transistor connected in common base, we can treat it as H parameter. We can easily apply H parameter model to CB, CE, CC. Now let us see what is the equivalent diagram for a transistor which is connected in CV, CB, CC configurations. This is a simple transistor. A transistor consists of three terminals. When we connect one terminal is common, we'll connect it as two ports. Let us consider a common emitter transistor connection. If it is this one, so here it is emitter connected to ground. It is nothing but common for both input port and output port. 1 dash is the input port, 2 dash is the output port. So that a transistor can be connected in a two-port network. Let us take a simple generalized, irrespective of whether it is CE, CB, CC. Take the transistor, a generalized transistor amplified circuit. So which has input port voltage, input port current, voltage and current between 1 and 1 dash, output voltage V2 and output current I2. If you consider it is a transistor, linear transistor element. Now we have a equivalent circuit diagram for two-port network. Consider transistor in the two-port network model. Then the voltage at input side is V1. The current at input side is I1. The impedance is called, we can now represent it with what is the general parameter for input side is H11, which is equal to now input impedance. So the name of this H11 now modified with the H11 to HI, input impedance. And then voltage source in series with voltage source in the equivalent diagram. H1 actual representation is H12 V2. H12 V2. What is called H12? We can call it as H12 is nothing but reverse voltage gain, so that we can represent with the R, small r. So where I represents the input impedance, R represents, small r represents the reverse voltage gain. Come to the output equivalent diagram in the H parameter model. This one is current source, so represented with the H2 to H21. That can be represented with the HF. What is HF? Forward current gain. That forward current gain represented with a small f, so that we can represent it. H11 can be represented with the input impedance. HR represents a reverse voltage gain. HR and H21 nothing but forward current gain. Forward current gain. And another parameter which is called H22. Now in this transistor model we can represent it with the output admittance. So we can call O nothing but output admittance. Output admittance. So there are four important parameters for representation, four notations which are used in the transistor as a H parameter model. One is HI, input impedance, HR, reverse voltage gain, HF, forward current gain, H0, output admittance. Input voltage we can call it as input voltage, input current we can call it as input current I1, and output voltage V2, output current I2. When we consider this notation of the transistor, then we can call it as this the two-port network equation V1 dependent variable, and I2 we can call it as, replace that H11, H12, H21, H22 with the transistor notation HI I1 plus HR V2 is equal to I2 is equal to HF I1 plus HO V2. This is the representation for H parameter model, H parameters in when we use transistor in the model. Now, the transistor, in spite of connection, we can consider this H parameter model notation is HI, HR, HF, H0. What if we connecting transistor in common base configuration or common emitter configuration or common collector configuration? Let us see one by one when the circuit, when replace this transistor and connected in common emitter, common base, common collector. H parameter model for common emitter configuration. So when the transistor, a two-port network, it is a two-port network, linear element transistor connected in two-port network. One port is 1 dash, 2 dash. When it is transistor connected in two-port network, in a common emitter configuration, this emitter is connected to ground, common for both ports, input and output port. It is a base terminal, so BE. So the current flow in the input port or input terminal is called IB because it is a base terminal. The voltage between base terminal with respect to emitter nothing but VB, and voltage between collector terminal with respect to a common terminal emitter VC, and current flow in the output port is called IC, like IC. So here four parameters, two voltages and two currents. One is VB, IB, and VC, IC. 4 parameters. Now, what is the equivalent H parameter network for H parameter equivalent circuit for common emitter configuration of a transistor when we connect a two-port network? So here we know that input is Kirchhoff voltage law network and output is Kirchhoff current law network. Input side a resistor in series with the voltage source, dependent voltage source, and output side a current source in parallel with the admittance. Here the input voltage VB, it is a common emitter configuration, we can represent it with the extra subscript VB. That is, we have to remember it. So everything is same. In a previous case, we have generalized transistor connected and its equivalent diagram. So it is H, if it is input impedance because HI, and it is common emitter configuration, that representation is represented with second subscript E, and it is HR and HRE VC. That H parameter second subscript represents E. All H parameter values represented with the second subscript with E, because which represents common emitter configuration. So here it is notation HIE, input impedance, suffix extra suffix small e, HRE, HFE, HOE. That extra suffix E represents the common emitter configuration H parameter model or H parameters. So here when we take the independent variables V1, I2, one is the input port 2. Here it is input port 2 terminal is base, so VB, and I2 represents the output port to current, output port current, where output port represents the collector. So we can represent collector current. I2 is nothing but collector current IC. VB is equal to, here VB is equal to base current IB multiplied by first H parameter HIE IB, which is just like H11 I11 input current కాబట్టి. So H11 I1 means IB input current IB plus H12 V2, H12 reverse voltage gain, HR is the reverse voltage gain, HRE is the common emitter configuration reverse voltage gain, multiplied by V2, here output voltage nothing but collector voltage. In this way we can represent VB is equal to HIE IB HRE VC. Similarly, output either we can understand by applying the Kirchhoff current law. IC is equal to sum of individual currents, where current nothing but HFE IB plus HOE multiplied VC, reverse voltage admittance multiplied voltage V by R, nothing but current. So HOE multiplied by VC. So you can also understood by this one. Otherwise, we can take output current IC HFE IB plus HOE VC. So here VB IC is a function of IB and VC. Similarly, when we take H parameter model for common base configuration, here it is base terminal is common for both the input and output, and the emitter terminal is input, collector is the output. Then input current is called IE, input voltage is called VE, output current is voltage is called VC, output current is IC. So here our generalized equation V1 I2, what is input voltage? VE voltage. What is output current? I2 IC. So VE IC is the dependent variables, is equal to H11 I1 plus H12 V2. What is H11? Is nothing but input impedance HI. It is a common base configuration, we can represent with a small b. So HIB, input current is what? Emitter current, HI, plus H12 nothing but reverse voltage gain. We can represent it in transistor model HR. It is a common base configuration HRB. So HRB. What is output voltage? V2 nothing but output voltage, collector voltage VC. In this way we can write the equation. So VE is equal to HIB IE, HIB plus IE is IE, a current flow in the impedance IE multiplied HIB IE, HRB VC. IC is equal to HFE IE HOB VC. That is called equivalent circuit for common base configuration model. Similarly, H parameter model for common collector. Here, for the common collector, output is taken at a emitter, collector terminal is connected to ground. Here it is connected to ground, but output will measure at a emitter terminal. Input terminal is called base terminal, so the current is called IB. Output terminal is called emitter, so the current output current is called IE. Common terminal collector, so VB VE. So here it is VE, and the current flow in the output terminal is called IE. So what are the parameters here? Input voltage IB, input current IB, input voltage VBE, input current IB. Similarly, what is output voltage VE, what is output current IE. So here input voltage V1 I2, our equations different variables. What is V1 base voltage? What is the I2 emitter current? So VB, IE. When VB, IE are the left side equation parameters, so remaining IB, VE, IB, VE are remaining parameters. IB, VE, IB, VE. In terms of IB, VE, we can write down the S parameter equation. So first parameter V1 is equal to H11 I1, H12 I2. So H11 nothing but input impedance, HIE nothing but input impedance. It is a common collector. We can represent it with C, small c letter. HIC, IB plus HRC, VE. Similarly, I2 is equal to H21 I1 plus H22 V2. What is I2? Output current. Here it is common collector, emitter current is output current. IE is equal to H21 forward current gain HF. In transistor model HF is a common collector HFC, and I1 nothing but input current base current. HOEC output admittance multiplied with the output voltage VE. So that we can get what is the H parameter model voltage VB and IE is equal to HIC IB, HRC VE, IE is equal to HFC IB plus HOC VE. So in this way we can draw the equivalent diagram of a transistor connected in common emitter, common base, common collector. Once we have awareness of these common emitter, common base, common collector transistor H parameter model, this transistor when we connected in any amplifiers, then replace the transistor with the H parameter model and connecting at extra input source resistance and load resistors and analyze it. What is the input impedance? What is the output impedance? What is the current gain? What is the voltage gain? We can measure. The main advantage of this model is so we can analyze accurate values of the parameters of the transistor amplifier, like input impedance, output impedance, voltage gain, and a current gain. So in order to get the amplifier accurate parameter values, we must replace the transistor, 3-terminal transistor with the H parameter model, so that we can analyze the transistor. It's very easy and accurate. So these are the representation of equivalent circuit diagram for common emitter, common base, and a common collector model in two-port network analysis using two-port network model. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.